Hi, everybody, and thanks for coming to the July Pony Virtual Users Group. Today we've got a presentation from Luke Cheeseman, who just finished his master's at Imperial College London on extending Pony with value-dependent types. Take it away, Luke.
Cool, thanks. So, as someone says, I'm Luke, and I'm going to talk to you about what I call Ponyta, which is value-dependent types in Pony. So, you guys all know about Pony. It's an object-oriented DAC model capable of secure programming language with loads of features such as actors, classes, and behaviors, and a really rich type system, which includes structural, nominal subtyping, union section types, and tuple types, a bunch of runtime features such as pattern matching and exception handling, and most importantly for this talk, generics. So in Pony, we can define parametric types like this array here, which is parametric on type A. We're defining the type of the element of the array. This lets us define like an array of U32 at line 6, or an array of string like at line 7, and these are fundamentally different types to one another. But this lets us only talk about the type of the element and gives us no way of talking about the size of the container. So with value-dependent types, we can define how large the container is in its type. So now we can define these types like the vector here, which is parametric on the type of the element and also on the size of the container. This lets us then instantiate a type like at line 6, where we have a vector of U32-4, and then we assign it 4 U32s. And this is fundamentally different to a vector of, say, U32-7 or U32-8. You can see this at line 7, where we have a vector of string 2. But we don't just want to be able to parameterize on the basic primitive types, like the integers and the strings and the bools. We want to be able to provide some really flexible value-dependent types. So here we have this matrix class, which is a multi-dimensional statically known structure, a fixed size structure. And so we have the first parameter is the type of the element, the second parameter is the number of dimensions, and the third parameter is a vector which represents the size of each dimension. So when we instantiate this type, like at line 6, we define the matrix of a U32 with 3 dimensions and the vector 2, 3, 4, and this defines a 2 by 3 by 4 matrix. So these are some of the things we can do with value-dependent types. But why would you even want them in the first place? It's really great that you can have all these things, but what's the benefit? So they actually allow us to obtain some more efficient data layouts as the compiler has more information to work with. You can provide better optimizations as the algorithm backend has more information to work with. And also, because the compiler has more information, you can have more static checks and remove some of your dynamic checks. So let's have a look at some of those. So recall for the matrix multiplication operation, C equals AB. This is well defined when A is an n by m matrix, B is an n by p matrix, and C is an n by p, and you get a result which is C, an n by p matrix. So using these value-dependent types, you can actually capture all of this in the signature of a method and only have this method only be callable when we have the correctly shaped matrix. So here with line 2, we define this matrix multiplication operation, which takes 3 parameters, which has 3 type arguments, n, m, and m, which are all U sizes. And then for the first argument, we expect a matrix, which is n by m, a second matrix, which is an n by p matrix, and we guarantee to return an n by p matrix. So when we try and call this, so let's first define 2 matrices, a 2 by 3 matrix at line 8, and a 3 by 5 matrix at line 9. And then when we call this at line 11, we pass the arguments 2, 3, and 5 to instantiate the multiplication operation. And then we can safely pass m1 and m2 because this is a well-defined operation. But what about when we want to try and multiply 2 matrices together where the operation isn't well-defined? So here we try and multiply m1 by m1. Now, this won't work because the arguments that we pass don't adhere to the type signature that we get from instantiating the function with 2, 3, 5. Furthermore, we can't actually provide any value arguments which would cause this multiplication to be callable with m1 and m1. So this is great. We don't have to have the extra runtime checks to ensure that the matrix operation is well-defined. But what would that look like without all this value-dependent types in the signature? Something like that. So we first off define the matrix as being an array of arrays as opposed to a matrix class. We first have to check that they're not empty, and then we have to check that they're actually matrices, so that the dimensions are all the same. And then we have to check that the multiplication is well defined. So the first dimension of the first array and second dimension of the second array is the same. And that's before we even get on to actually doing any of the matrix multiplication. So this is really a pain because we'd have to then do all these dynamic checks every single time, whereas with value-dependent types, we do it once at the compilation time. So that's some of the stuff we can do with value-dependent types and some of the motivation about why you'd want them. But before I get on to how I've implemented them and things you can do with them, I'm going to talk about what the compiler looked like before I started. So you guys probably know that the compiler works as a multi-pass compiler. So you start with the Pony source code, and then you parse this to some internal AST representation, which is important, and we'll talk about more later. And then you sanity check it in the syntax pass to ensure it is the syntax. You have the names pass, which ensures that types are well defined and they don't clash. You have the traits class, which includes the methods in the classes which inherit from traits. The extra pass, which is in charge of type checking, and finally the IR pass, which generates your final executable LVMIR or object file, for example. So the value-dependent types implementation comes down to three main components. So firstly, we have the compile-time expressions, then the value-dependent types and their subtyping relationships, and finally some containers that are built that rely on value-dependent types. So we'll start off by talking about compile-time expressions. So some languages like C++ already support a notion of a compile-time expression. So we start off by looking at what C++ does for compile-time expressions to see if there's any lessons we can take away and apply to Pony. So here's an example of a Fibonacci function which can be evaluated as a compile-time expression. So at line 1, we define the const for int fib int n, and this defines fib to be a compile-time method. Then at line 11, we define the const for int x and assign to it Fibonacci 10. So what this will do is the compiler will go away and evaluate Fibonacci 10 and assign that value to x. And you'll note that this context keyword crops up every time we want to do a compile-time expression. So we consider whether we need such a keyword when we have it in Pony. Turns out we don't. All we do in Pony is we just have this hash directive which tells the compiler to go away and evaluate the compile-time expression. This is way less invasive than the context keyword that we have to use in C++. And whenever a developer wants to be able to see if they can evaluate the expression at compile time, all they need to do is whack a hash in front of the expression, and the compiler will go away and figure it out. You don't have to go and retrofit all your existing code to have the context for keyword. So that's really great. We have this really flexible programming idiom, which was able to just be achieved with just one keyword, a syntax introduction. But that was quite challenging to get it to be like that. So what have we changed in the compiler up to this point? So we've only so far changed the parsing pass to allow for the hash syntax, and also I'll mention here that we changed the type parameters to allow for a lowercase identifier in terms of allowing value parameters. We've also slightly changed the syntax pass to sanity check some of the new syntax. So we've spoken about what compile-time expression sort of looks like, but what can the compiler actually evaluate? So we start off by saying that primitive literals, such as integers, floating point values, booleans, and strings, they're all compile-time expressions. They're literally in the source code, so the compiler definitely has access to them. And furthermore, the basic methods, such as add and, which are defined for these primitives, they're also compile-time expressions. So these work off using inbuilt C methods in the compiler, which transform parts of the AST. And we'll talk more about this later. And so well and good if you can have values which you can use as compile-time expressions. We've seen so far you can have your vector, but what we really want to be able to do is reuse some of the expressions later on. What you want is a compile-time variable. So as you probably know, Pony has a distinction between a single assignment and reassignable name. So let constants may only be assigned to once, whereas var variables may be assigned to multiple times. So if we assign to a let constant a compile-time expression, like at line 1, we assign the compile-time expression 3 to x, we should be able to reuse this later on, as the compiler should know what the value of x is, and it can't, because it can't be reassigned and the value has been evaluated to compile time. And that's exactly what we do at line 2. We assign the expression x plus 7 to y, which will be rewritten to 10. But we can't always just have let variables as compile-time expressions, because the right-hand side of the assignment might not be known to the compiler. For example, here we do rand.next, and we wouldn't know what that would equate to. So we can't have that. So it's great. We have a form of using compile-time expressions in later expressions and building up more complex compile-time expressions. But that's only the let constants. What about the vars? So a var, you can't always track the value of a var variable. For example, here we define I to be equal to 1 at line 1, and then we increment it on each iteration of a while loop. And then at line 5, we say, okay, I want I to be equal to I plus 1, but the compile-time expression, I plus 1. But it's not really, you couldn't really figure out what the compiler should rewrite that expression to, so we declare that to be forbidden. And this relates back to in beta reduction, for example, I would be a free variable, so you couldn't really reduce this expression. And this idea of beta reduction I'll come up on again later. But sometimes the compiler could know what the value of a var variable is. If the var variable has been declared inside of the compile time expression and all the updates to the variable are known in the compile time expression. But whenever you use that expression, that variable inside of the compile time expression, the compiler should be able to use that and evaluate it to some meaningful value. So here we have the hash on the outside of the entire expression, and we define I to be 1, result to be 1, and then we calculate the 10th factorial number, incrementing I on each iteration of the loop, and finally put in the result. Now this will rewrite all of the entire expression here into just the result node, which, as I said, would be 10 factorial. So this means that I and result, the scope of them are exclusive, incorporate only to the compile time expression. You can't use them outside of this. So that's great. We have some way of using iteration in compile time expressions. So we had a couple more rules. The let constants, which have been assigned compile time expressions, can be used as compile time expressions, and that the var variables declared within the compile time expression can be used within that compile time expression. So now we have literals and variables as compile time expressions, but what we want to do is allow Ponyta developers to use really flexible value-dependent types and construct some really complex compile time expressions which they can evaluate using their own types. So what we really want is compile time objects. So take an example here where we have a map of keys of type K to values of type V, and we also provide a default value in the type of type V. We then go on to define a type student, which has a name field and an age field, and then at line 13, we declare a map of string to student val, where we provide the compile time object student Luke 22 as the default value. So you'll notice here that the value type has student val. Now this is important because we want the value type arguments to have this deep immutability so that the compiler can use the value of the compile time object anywhere within the definition of map and guarantee that the value is going to be exactly what it expects. If you had ref, for example, this wouldn't be particularly useful because you'd only have to say, perhaps use the global object address of the compile time object. So we say only val. So this is what a compile time object looks like. So how do we actually incorporate this into the compiler? There's no current way of representing the compile time objects, such as there are with string and bool. So what we do is we extend the AST representation for compile time objects. And all this means is that a constructor for an object as a compile time expression just builds the AST representation of an object. So I'm going to show you an example of that now. So we've got this student Luke 22 from the previous slide. And what this will do is this looks like the constant object node subtree. And on the leftmost subtree is the name, which is the hygienically created name for the object. So this makes the object uniquely identifiable throughout the rest of the AST and allows us to use identity equivalents between any two compile time objects to test whether one object is the same as another. And furthermore, this gives us some global name by which we can use in the LLVM part of the compilation so that we can refer to these global objects. And moving quickly on through the rest of the constant object, we have the members subtree, which is just the name and the age field. And finally, we have the type, which is student. So that's great. We have compile time objects. We have, so it's great, you have compile time objects. And we had another rule that classes defined without using var fields may be instantiated as compile time objects. So I say without using a var field because a var field will allow the class to be mutable. And so far, we don't allow mutable objects, something we would like to later on, in the same way that if you track the assignments to a var variable, you should be able to use that value later on. But as I said, it's something we don't yet support. So we have all sorts of things now. We have primitives, we have variables, we have objects. But what we're going to be able to do is allow some way of a developer to use a method. So if we look here at line 2, we define this fact method that's got a suspiciously familiar looking piece of code as the body. And it turns out that the parameters are just let constants. So if we map the parameter to a compile time expression that's been evaluated, we can just evaluate the rest of the body as if it was anything else. So that's great. That gives us our final rule for this main body, which is that methods built using these rules and using compile time values for arguments are also compile time expressions. So this page here makes up the bulk of what I consider to be the important parts of compile time expressions. And I'll quickly talk about a few more rules for compile time expressions that I don't have provided some examples for. So field lookups on compile time objects and compile time expressions, they're also compile time expressions. Actors and behaviors can't be used in compile time expressions, and this is because behaviors are an asynchronous concept and the compile time expressions execute sequentially. So to incorporate these doesn't really make a lot of sense. And we don't really want these global actors that are available throughout all sorts of types, so we just allow them as well. Finally, compile time expressions must be recoverable to val capability values. So this comes back to this deep immutability that I mentioned earlier, that for the compiler to be able to reuse the compile time objects that we created, we need to ensure that they wouldn't have changed during the runtime execution. Otherwise, this would introduce some sort of weird ambiguity as to what the right value should be. So we ensure that they must be val capability values. So that's great. There's a bunch of rules, and we've spoken about some of the really cool things that we've been able to introduce be able to evaluate compile time using the semantics that are provided by defined for the Pony dynamic runtime. But what about other things? So it turns out we've stated I've just written on the wrong slide. Sorry. So the compiler needs a way of evaluating expressions at compile time. So when do we evaluate these expressions? How do we evaluate them? So could we generate some executable code and run that and then decompose the result into some value? Or could we evaluate some internal representation? So let's first off discuss when we evaluate compile time expressions. So I mentioned earlier that the extra pass handles type checking, and I also mentioned that compile time expressions can appear in types. So what we initially did was that we evaluated all expressions during the extra pass. But it turns out that when we extended compile time expressions to be able to evaluate methods, some of the methods hadn't yet been type checked, and we only want to evaluate type-safe methods. So what we do is we move the evaluation into one later stage, it's the IR pass, and this actually gives us the benefit that we only evaluate reachable expressions. So the Pony compiler does a reachability analysis starting from main and finding out which methods can be reached. And we only evaluate the expressions in these methods that you can reach. This means that we avoid the overhead of having to evaluate expressions which have no effect on the overall the resulting program. So how do we evaluate the compile time expressions? So the compiler parses the Pony program to an internal AST representation, and then evaluating the compile time expression is in essence some sort of beta reduction across the AST. So what I did was I built a Pony expression interpreter. So let's have an example here. So here we have the assignment to x of factorial 3 plus 7 as a compile time expression. So this originally builds the left-hand subtree, where we have this top-level assignment node, the let x subtree, and then the entire compile time expression subtree, which is calling fac on this with the argument 3 plus 7. So what the interpreter will do, it will just go and it will find the hash subtree and just rewrite it to its final expression, as you can see on the right-hand side. So I've spoken a lot about what you can do with the compile time expression now, and how and when they're evaluated. But these compile time expressions starts off as something that we use just to support value-dependent types. But as we continued building them up, we realized they became more and more powerful, and a powerful programming construct in their own right, and allows us to introduce a bunch of new concepts and solutions for developing in Pony. So let's start off by talking about compile time errors and what happens when you encounter an error in a compile time expression. So error in Pony is a sort of method of handling exceptions. You can pass these up and cause partial functions and catch them using try-else blocks. So the first line we define this assert primitive with a single apply method, which takes a boolean, and then if this boolean doesn't hold, then we error. This means that the function has to be partial. And then at line 5, we define foo, which dynamically asserts false. And because assert can throw an error, we make foo partial. Line 8, we define bar, and we assert false statically. But what does it mean to us if the error occurs statically? So we could just replace this with an error, but this isn't really useful because it just means that you'll error every single time you call bar. So what we decided to do was that if a compile time expression results in error, then compilation fails. This also means, though, that bar doesn't have to be partial because the error can't have occurred at runtime, so we don't need the partialness of the function. And just to reiterate a point I spoke about earlier, the compilation will fail when we call bar at create. So when we do the reachability analysis, we'll find that bar can be reached, so we go and evaluate the assert, and then it will fail. Another problem that one of the Pony developers had is they wanted to split long strings over multiple lines, but only generate one string literal. The Pony doesn't have any way of doing this, but with compile time expressions we can. So here we have hello plus blank plus world plus bang, and without the compile time expression, or the hash here, we generate 4 string literals in your data segment, and this starts to get a bit annoying if you have lots and lots of strings hanging around. But if you put the hash in front of it, this will be rewritten in the AST to a single single string literal, and the developer will have the convenience of being able to break out for multiple lines. So it's great. We have a bunch of new things we can do with the compile-time expressions, and they've become really, really powerful. It's interesting to see where they've gone. So that's all I want to talk about for compile-time expressions, and now we'll move on to value-dependent types. So recall this array class, which is parametric on type of its element, and recall the vector class, which is parametric on the type of its element, and also on the size of the container. Now, with new types requires us to consider new subtyping relationships, precisely what it does mean for one value-dependent type to be a subtype of another. So we start off by looking at how Pony deals with subtyping on generics. So Pony is type invariant with generics when we're talking about classes. Specifically here, an array of U32 is only the type of the an array of U32 can only be assigned to array of U32. We can't assign an array of U32 to an array of string because the right-hand side parameter is not the same as the left-hand side parameter. And we use this lesson and we apply it to the subtyping value-dependent types. So we say that value arguments must be syntactically the same. So to give an example of this, at line 2, we define foo, which takes two type arguments, n and m, both of which are U32s. And on line 3, we assign a vector of size n to a vector of size m. Now this will fail at compilation because n and m are not syntactically the same. Now this differs to how C++ would handle this issue, because C++ would only check this on an instantiation. So we would allow this definition, and then if we instantiated foo with 3 and 3, then it would work. If only we disallow us at the template level, and we save ourselves having to do a bunch of type checks on every single instantiation, thus saving some compilation time, which is great. And I'm going to give a couple more examples here at line 7. We can assign a vector of U32.3 to a vector of U32.3, but we can't assign a vector of U32.3 to a vector of U32.7. 3 and 7 aren't syntactically the same. So what about expressions that would evaluate to the same value? So here we try and evaluate a vector of 2 plus 1 to a vector of 3. Now you'd really expect this to work and you really want this to work, but I said that expressions must be syntactically the same. So what we first do is we try to evaluate expressions used to instantiate types. What this means is that a vector of U32 2 plus 1 is a subtype of vector of U32 3. However, this means that we have to do a bit more evaluation earlier on. So we go back and add some evaluation to the expert class, and we try to evaluate expressions which appear in type arguments, but we still do all other expressions evaluated in the IR pass. So that's compile-time expressions and value-dependent types covered. So now we'll go on to describe some of the containers that I built which rely on value-dependent types. So we'll come back to this array class, and here array is a contiguous resizable memory store, and all the elements for an array are stored externally and accessed indirectly. Now it's resizable in the way that at line 6 we can define an array which has 2 elements, and then we can push a third array, and this causes the array to grow. This also means that the elements have to be stored indirectly so that we can change the size of the memory. This gives us a layout that looks something like this. So here we define the array of string, which has 2 elements A and B. And the first element in the array data structure is the script table, which includes the V table and trace function and so on. And it has a field which describes the size, which is the number of elements in the array so far. Alloc, which is the amount of space allocated for the array. And finally, a pointer, which points to where in memory the elements actually are. And then we have the actual elements somewhere off in memory, A and B. What about a vector? So a vector is a contiguously statically known fixed size memory store, and elements are stored internally with no direction for accesses. Now we can do this because it's fixed size, so we don't need this resizable issue, so we don't need to store externally. So this layout looks something like this. So we define the vector of string 2 with 2 elements A and B, and we are able to only have the script table and the 2 elements. So here we've saved ourselves 2 fields and an entire level in direction. So this is great. We can optimize our data structures and get better performance. But it's all well and good me just saying that, so let's actually show you how this performance increase happens. So I benchmarked the new data structures using the Floyd-Walsh algorithm. So if those don't know, that finds the minimum weight path between any 2 points in a weighted graph. The benchmarks I used so initially the graphs were initialized randomly using a repeatable random number generator. And I adopted different representations of the underlying graph. This vary between a one-dimensional, two-dimensional array and a one-dimensional and two-dimensional vector. Now, I did this benchmark in particular because some early Pony benchmarking showed a significant overhead of using a two-dimensional array for the graph representation over a one-dimensional array. So this is visible in this graph here. So you notice here that the two-dimensional array has a stark difference compared to the one-dimensional array. In particular, the one-dimensional array was 1.41 times faster than the two-dimensional array. The most important thing here is that the vectors are way better than the arrays. Even the two-dimensional vector performs better than the one-dimensional array. In particular, the one-dimensional vector performs 1.24 times faster than the one-dimensional array. Now, on the left here, I've plotted this with a log scale to show you how consistent it is, but on the right, I've plotted it without log scale just to show you how much better it is. So this is great. We've got this fantastic new data structure. But what else can we do with vectors? Well, let's consider joining two vectors together. So here we define this add method, which has one parameter m, and then we take an argument of that, which is a vector of how this is a of size m, and we return a vector of how this is a alias and is of size n plus m. This is great. We can define compartment expressions in terms of the templates, and these will be evaluated when we instantiate the vector and add method. And this is great because we can also define vectors whose size is defined in terms of other variables, and we can build new value-dependent types out of existing value-dependent types. So to give an example of this, at line 10, we define a vector of 2. At line 11, we define a vector of size 4. And at line 12, we do v1.add instantiated with 4, pass in v2, and this gives us the vector of v36. So it's great. We can join these vectors together, and we don't lose any information about their size. So that's the vector. What about this matrix? So recall that the matrix is this multi-dimensional static and fixed size structure, and we get this information by passing in the type of the element, the number of dimensions, and the size of each dimension in this dims parameter. And we represent the underlying structure of the matrix as a one-dimensional vector. We do this because it was one of the best performances that we had in the Floyd-Warshall algorithm, and also it's one of the easiest representations to obtain. And what's coolest about this class is that we were able to do the entire matrix class in just Pony. We don't need any compiler intrinsics. So here we represent the underlying vector we embed it, and then we calculate the size of the vector when we instantiate it using this alloc method, which goes through and multiplies these all together. So it's great. This class really shows off the flexibility that you can get using these compile-time expressions and value-dependent types. So here we'll instantiate a couple of them just to show off how flexible this class is. So we have this matrix of a 2 by 2 U32 matrix at line 6, a 2 by 3 by 4 by 5 matrix at line 9, but line 12 is a type error. We can tell that we want 4 dimensions, but we only provide 2. So it's really cool. It really shows off how flexible this matrix class is. So how are these elements actually laid out in the matrix? So we spoke about how it's a one-dimensional vector, but how the elements are actually laid out is all to do with how you calculate the address of when you index into them. So at line 3, we define this apply method, which takes as an argument a vector of u size, which the index into each dimension. So notice here that the vector has to be of size n, so we can only provide a completely correct index vector. And then using the calculate address, what we do is we obtain a row major order for the elements of the matrix. So this means that if you had a bunch of nested for loops, the innermost for loop changes most quickly when you're indexing into the matrix, say if this was an array of arrays. We chose this one over the other alternatives like a column major, or there's others like mortar or just random indexing. So the row major order looks a bit like this. So you'll notice that the rows of the innermost dimension are together. So we have 0, 0, 0, 0, 0, 1, 0, 0, 2, and then the second index increases and the next row is together. So here we have an example where we define the 1 by 2 by 3 matrix, and then we have to index to get the 0, 1, 0 element. So I'm now going on just to benchmark them. Now you'd expect, so I compare the one-dimensional vector with the matrix, and you'd expect these two to perform exactly the same, considering how underneath the matrix is essentially a one-dimensional vector. But when we actually benchmarked it, it turned out the one-dimensional vector was 25 times faster than the matrix, which isn't great, and it's something that we're going to look into to try and fix. We have a couple of ideas of what happened there. It's possible that the calculation to get the indices isn't correct and maybe obtaining some bad performance. Another possibility was that in the Floyd-Warshall algorithm, the one-dimensional vector to obtain the correct index, the calculation was in the Floyd-Warshall algorithm in the loops, whereas in the matrix it's in the class. And it's possible the LLVM backend is missing the optimization because the calculation isn't as clear to it. But it's something that we're going to look into and try and fix. So that's how the benchmarking for the data structures turned out. So what about the benchmarking for the compilation times? So we compare the array Floyd-Warshall benchmark with the vector benchmark to see how much overhead we get in using these value-dependent types. So building the array benchmark took about 2.5 seconds, and building the vector benchmark took about 2.75 seconds. So it's great, we only got a 0.25 second overhead for using the value-dependent types. But something that wasn't great is we compared the original Pony compiler against the Pony compiler with value-dependent types on a benchmark which didn't even use value-dependent types. We artificially inflated it to be quite a large program, but you'll notice it's about 17 seconds using the original Pony compiler and about 21 seconds using the new Pony compiler with value-dependent types. So this is something that's probably a result of when we do the reachability analysis, we do a depth first search through each method to see if there are compartment expressions inside of them that we need to evaluate. This is something we think we can avoid because there's already these depth first searches in earlier passes of the compiler. So we can probably mark these methods to say whether they have a compartment expression inside of them and save ourselves some compilation time. But it's definitely something we're going to look at fixing. So that's compartment expressions, value-dependent types, and the containers spoken about. And I hope you really enjoyed that bit. And what I'm going to talk about now is where you could go with all these things. So firstly, we probably want to improve the performance of the matrix and the compilation times. But you could also build libraries for vectors and matrix arithmetic, as we've seen so far with the matrix multiplication operation. It would be nice to go on to have mutable compile-time objects, like I spoke about earlier. And what I'm going to wrap up on is value constraints and template specializations. So in Pony, we can already have type constraints for a value. But what about when you want to ensure that a value is less than a particular size? So we'll come back to this assert example that we used earlier. So here we have this apply static on line 4, and then n is the index here. And then at line 5, we assert that n is less than the size of the vector. So it's great, we can ensure that the index is less than the size of the vector, but is there a more fluid way of doing it? So something we could do is say at line 4, where we have value constraints. So this will say that n belongs to some family of values where the values are of type usize and all the values are less than size. So this is great as it looks a bit nicer and also gives us a way to remove some of the runtime checks as you don't have to dynamically assert that the index is less than the bounds of the vector. So what about template specialization, which I mentioned earlier? So have a look here at the Fibonacci sequence, which is defined as a template rather than as a function with an argument. So here we have that on line 6, we call Fibonacci of n-1 plus Fibonacci of n-2. But when we call Fibonacci of 10 at line 10, we'll cause this infinite instantiation issue because even though the else branch isn't taken when n is 1, the compiler doesn't know that, and so has to instantiate the n-1th case. And in fact, it will just have to instantiate Fibonacci for all elements of usize, which isn't great. Quickly compare this to a compile time function, whereas this will terminate because when n is 1, we will not hit the else branch and we'll just return 1. So how could we avoid this infinite instantiation problem? So if we could provide the base cases, we could avoid it. So this is something we do here at line 2, where we have fib0 and fib1, which just go to 1. And then when we hit the n is 1 case, when we instantiate fib10, when we get down to fib1 in line 4, this definition will be provided and we won't have this infinite instantiation. So it'd be really cool if we could work to get something like this using these template specializations. And then we'd be able to perhaps combine the template specialization and value constraints to get an even more succinct definition of fib, for example, where we can say that fib where s is less than 2, we can just default to 1. In all other cases, we behave like normal. And this will be able to provide some different definitions of methods when different predicates are satisfied. So this would be a really cool extension that if we could get it working. So just to wrap up, to add these value-dependent types and compile-time expressions took about 4,700 lines of new code to the Pony compiler, test suite, and standard library. I went through many iterations and revisited the features to get this as it is at the minute. We built a complex new type system and provided a bunch of new programming idioms. I will merge my work into the Pony mainline compiler once I've finished the merge with the current master branch and fixed some of the issues that were a result of that. And so to conclude, the value-dependent types provide a great flexibility for defining types and allows the type system to make more assertions and build some better representations as the compiler's got far more information. These compartment expressions can give the ability to evaluate expressions statically, nice to speed up runtime as we evaluate, put some of the inputs onto the compiler instead of onto the runtime, provides us with a way of defining some new programming idioms, and finally develop some efficient containers which have shown using benchmarking their performance improvements. So thank you for listening to my talk about value-dependent types in Pony, and are there any questions?
I don't have a question. I just have a comment that's all really friggin' awesome, and I can't wait for it to get merged.
Thank you.
Well, I agree.
Thank you.
So when are you going to file the PR, Luke?
I'm fixing the merge at the minute because it broke.
Okay, great.
But then I will fix it. Once I've fixed that, I will submit a PR.
Fantastic.
Who gets to review that PR?
I've been reviewing that PR for some time now.
I'll do my thing of looking to make sure that there's a change log entry.
Good talk, Luke. Thank you.
Thank you.
Yeah, thank you very much.
Thank you.
Awesome. So if there are no other questions, we should have another one of these coming up. I think it was sometime in the next 3 weeks or so. I'm not sure. It's mostly scheduled, but George, who's on this, needs to send me an email to finish scheduling it. But so.
Yep. Sorry. I will do that in the next few days.
All right. So 2-3 weeks, I think it was, and we'll have more fun. Thank you, everyone, for coming, and thank you very much, Luke, for this. It was awesome.
Thank you.